Hello everyone, welcome back to lesson number 32, where we're talking about work for BC Calculus. And in this video, first thing I'm going to start with is doing another right circular cone problem, where we're given three different conditions. So we're going to set up three different integrals, and then I'm going to talk about a spherical tank. So in example 8, it says a water tank is in the shape of a right circular cone. And so what I do with a right circular cone is I go ahead and draw the x and y axis, and I always make my cone, the corner of it or the bottom of it always be at the origin. So that's just probably the easiest way for me to tell you guys to do that. So I always make the corner of the cone be at the origin, and then I go ahead and write that the height of the cone is 30 feet and that the radius is 8 feet. And so I want to find the work required to pump out all of the water over the tank. And it's also given me that the weight of the water is going to be 62.4 pounds per cubic feet. So first thing that I'm going to acknowledge with this problem is the fact that if I were to do a cross section of this, I would actually have cylinders. So I would actually draw a cylinder, if you guys will, right here. And so I need to find the volume of this cylinder. Now I just want to tell you guys again that remember that in order to find the work that's involved from A to B, we want to find the force times the distance. The force, again, is going to be the volume of the cross-section times the weight of the fluid, the liquid. And so we're already given what the weight is. So this is going to be 62.4. This is going to be 62.4 pounds per cubic feet. So I got to figure out the volume. Well, it's a cylinder. So the volume of a cylinder, and for all right circular cones, it's going to be a cylinder. It's going to be pi r squared times height. The delta h, so the delta y is going to always be your height, because that's how thick the cylinder is going to be. So this is going to be delta y, which is going to be the height of your cylinder. The radius is going to be this distance right here, right? The distance of this. Well, we learned back with area and actually with volume that it's going to be the right curve minus the left curve. So I got to find the equation of this line, and it goes to the point. It goes to the point 8, 30, right? Because 8 units to the right or 8 units to the right up 30. So it goes to the point 8, 30 and the origin. So I know the equation of this line is going to be, well, the slope is going to be 30 over 8, right? So it's going to be y equals 30 over 8x. And I know that, again, based on what we've learned in this unit, that it's a right curve minus left curve. So I have to rewrite this as x is equal to, right? X is equal to 8 over 30y. And so now I've got the equation of this line, and we know the equation of this is simply x equals 0. So right minus left. So the radius of our function is going to be 8 over 30y. All right, it would just be this function minus this function. So that's the radius of our function. I have all that I need. I know this looks very jumbled. I have all that I need. Now solve these problems. So the first question says, if the tank, I can't read, is filled with water to a depth of 20 feet. Now remember, we want to take it all over the tank. We want it all over the tank. So we're going to integrate here, and our water depth is at 20 feet. So we're at 0, and then we're going to be at 20. So that's just going to tell us what our integration is. So 0 to 20. Then I'm going to go ahead and write the weight down. So this is going to be 62.4. I'm going to multiply that by our volume, right? Our volume. So here's our volume. It's pi. We already know what our r is. So we're going to go ahead and do 8 over 30. And yes, you could simplify that if you want to. Y squared. And then our height is going to be our dy. So what I've written right here is going to be our force. So this right here is the force of our in order to push our water out. Then the only thing left for us to do is find our displacement. We need to figure out what this d is. Well, this is going to tell us how far we need to go to push all the water out of the tank. So just like before, this is going to be some distance y. Again, using the shell method, we know that if we look at this rectangle, it's parallel to our axis, so this is y, and we want to go to a distance of, over the top of the tank, we want to go a distance of 30. So we want this. This is the d, and the d is going to be 30 minus y. So this is going to be 30 minus y. And so this is going to be the actual displacement, or our d, for our problem. So this is going to be our force, and this is our d. All right. Now, let's look at the next part of the problem. So let me make sure my eraser is a little bit bigger. And one more thing we can just do really quickly that I could acknowledge before I get to the next one is look at units. Because remember, we want our units to be pounds, feet, right? Pounds, feet. So this is going to be in pounds per cubic feet. This is in feet squared. So if I were to go ahead and multiply these together, this is going to cancel, and I'm left with 1 down here, pounds per foot. The dy is also going to be feet. That's going to cancel with this. So now I'm just left with pounds. And then this is going to be also feet. So I'm left with pounds, feet, which is exactly what I want. So use the units to actually figure out, did you accidentally, did we forget the square, the radius, or did we forget the displacement, or other stuff like that? And pi is just obviously a number, so we don't have to worry about the units for that. So what is different between this question here and now B? The tank is full. So the only thing that we're going to change is actually this value right here. This is simply going to now be 30. Because again, this lets us know, where is the water initially? Well, it starts at the bottom of the tank, and now our water is full. So the whole tank is full. So here we're 2/3 of the way up, right? It's just a depth of 20 feet. And so if this had said a depth of 23 feet, it'd be 0 to 23. Nothing else is going to change in this problem. We still have our cylinder. It's, it just, the difference is that now our water level is at 30. So we're still going to have our volume of our cylinder still going to be the same thing. And then our displacement is still going to be the same as before. We still want to go 30. Now, part C is asking us to figure out, well, if the tank is full and the water is being pumped to a height of 10 feet above the top. So since, again, it's full, we're going to do 0 to 30. Well, this 10, we want to now move it 10 feet above. We want to do it 10 feet above this. So this is going to be 40, right? So 10 feet above 30 is 40. So the only difference here is our displacement. Again, ladies and gentlemen, the weight of our water doesn't change. Our volume of our cylinder still doesn't change. Our dy doesn't change, but now our displacement changes. We want to go, again, if this distance is y, now our d is going to be from here all the way to our rectangle. So that's going to be our d. So our d is going to be 40 minus y. So that's going to be the difference between this. And again, I can use the problem, say that if, we're at the very bottom of the tank, then if I plug this into here, I have to go 40 feet to get out of the tank. Well, 40 feet to get out of the tank plus an initial 10 feet. And if I'm at the top of the tank at 30, I'm traveling, my water still has to go up 10 more feet. So actually, I'm thinking this is a good place to stop this video so we can move on to another example in the video number 4. So I hope this is helping. The better you see it, the more you practice it, the better you're going to become at it. I'm hoping now 3 videos in, you guys have a better understanding than you did maybe in video number 1. So I'm going to stop talking here, and I will see you guys in our 4th video where we do another shape.